Well, it gives me great pleasure to welcome to Athens. I'm not sure it's for the first time or not. I'm not sure if you've been to Athens. First time in Athens. Give him a super extra warm round of applause to Stephen Holden from the Python Software Foundation. And the Global Stress Index, which is something super interesting I just heard about, and he just showed me his heart rate, and my heart rate is just as crazy. So yes, let's do that very quickly. Do you guys remember this? The guys that were here yesterday? We're running an electronic question system, so if you want to run question, put a question to the speaker straight after the talk, scan this QR code, it'll take you to a web app, and you can put your question in through there, and that saves me from running up the stairs with the microphone. But I will do that if we need to. And everybody, Steve Holden, thank you.
Kalimera, everybody. Good morning. Isn't this a magnificent auditorium? I think so. It's really nice in a country where speech is still regarded as an important medium. So it's a pleasure and it's an honor to be opening Python Day on this very first Open Conference. This is my first visit to Athens, but I sincerely hope it's not going to be the last one. I'm Steve Holden, not Stephen, by the way, usually, always Steve. And for 20 years, my life was intimately bound up with the Python language and the mission of its foundation. I notice I was billed as representing the PSF, so I should point out that I no longer have any formal position with the foundation, and so I don't speak for it, but I do, however, still strongly subscribe to its mission. This particular picture was taken in the Amazonian jungle while I was on a trip to Argentina and Brazil to speak to those two countries' annual Python conferences. So Python has, from time to time, been very good to me. This is the mission of the Python Software Foundation in abbreviated form. There's a longer version too. And today's audience, I think, demonstrates that that mission is being fulfilled. It's strange the way talks develop. After I'd decided on the title of the talk, I was asked to talk, or to focus at least, on Python's design. So if this talk isn't what you were expecting, don't worry, it isn't really what I was expecting either. But I hope it'll be of interest to all of us, me included, but certainly to a Python and a cloud audience. Python audiences are usually friendly anyway. You might wonder what makes someone so passionate about a programming language that they decide to dedicate such a large amount of their life to it. And in order to explain that, I'd like to go back to the beginnings of my passion for programming. Oh, hello. That's interesting. That was a button I hadn't rehearsed with on the controller. So I started programming before the majority of people in this room were born. You can check this, the date shortly. It's a somewhat humbling thought because 50 years' experience has taught me that I still make avoidable mistakes on a daily basis. It's also quite a happy thought because after a career mostly spent building software systems, it's still something that I really enjoy doing a great deal. And so from that point of view, I've always considered myself incredibly lucky. The theme for today is the practical applications and the theoretical foundations of Python. And I was happy when I saw that because I've always believed that practical experience should come before theoretical knowledge. It isn't appropriate to get too deeply into practical details in a keynote address, although I will be showing you a bit of code. But if this is a typical Python conference, I'm sure that you're going to get plenty of technical details anyway and practical knowledge. So if you're new to the language, I hope that you'll both be fascinated and impressed by what it can do. So despite its title, this talk ended up being more about Python's fundamentals than the many uses that it's being put to nowadays. As a child, I was fairly carefree and reasonably clever, but I was never particularly happy at school. I much preferred to take apart old clocks and discarded radios and televisions that I either found lying about or bought at jumble sales. They looked a lot like these pictures, although they were invariably a lot dirtier and grubbier. The clocks were fun because you could pretty much see how they worked. I never actually managed to get one back together again and put it into working order. But the electronics, that was quite different. What were all these weird-looking parts? What did those funny glass bottles do? There weren't any transistors in those days. How did these things all work? I left school at 15, and I became a trainee production engineer in a TV factory with ambitions to work in technical development. Unfortunately, I soon learned those jobs were reserved for the sons, not the daughters, of course, but the sons of the management, so I should forget about those. So I spent a happy year or so attached to the work-study department, learning about factory life, all the processes of TV manufacture. At that point, the company told me it had decided that I should train in mechanical engineering. What? I started looking for another job, although while I was looking, I did actually learn how to file a flat surface on a bar of metal. Almost by accident, I found a job at my local university in the computer laboratory. They'd advertised for a junior technician, so I thought I'd be working on the hardware, but actually what they wanted was someone to operate the computer. So a lot of my time was spent keeping the computer running, but I also learned Algol 60. And so in March 1967, I wrote a simple program to print the squares of the integers from 1 to 10. Please raise your hand if you were born after that date. Thought so. Okay, computer operations were very different in those days. The computer I was working with only had paper tape peripherals. So you had to key your program in on a machine called a flexor writer that punched it onto tape. The compiler itself was a large program. It was contained on two 20-centimeter reels of tape, so you'd read those in. Tape readers were actually quite fast. They used to go at, I think, 2,000 characters a second. So we had to read that into memory, and the compiler would then read each program, and it would punch out a resulting executable program if you were lucky. If you weren't, then you'd get a tape containing compiler error messages, which you had to put through a flexor writer to print out so that you knew what was wrong with your program. If you've ever had to edit paper tape, you will never complain about Emacs or VI again. So once you'd got your binary output from the compiler, you had to take each executable program, read it into memory, link it with the library routines, that was another 20-centimeter reel of tape, and run it. And then if you were lucky, it would run and it would punch its results out on tape. You would then put that tape through a flexor writer and finally get your printed results. It wasn't a very convenient process. Certainly wasn't agile in any sense of the word. So the second program I was asked to write was to convert information on 8-hole paper tape, which was what we principally used, to 7-hole tape, so that we could use an older flexor writer that used a different code to print the output when the computer was busy. Algol wasn't particularly good at I/O, so I had to learn assembly language to write this program. The idea that the same information could be represented in different ways was quite an intriguing challenge. Now, Algol 60 was a fairly limited language, and certainly paper tape was a fairly limiting medium, but they were quite enough for a beginner. In my second and third computing jobs, I got to use PL1, which had features for describing record structures, and I was introduced to disk file I/O and index sequential file access. And while programming commercial systems, I started to read about the research that was going on into things like compilers and new languages like Lisp and Snowball, as well as research into different types of computer, like stack-based architectures and that kind of thing. Those are pretty heady times. I realized that real-world objects could be described or represented by data structures, and that real-world relationships could be represented by references between the structures. In essence, any information could be represented in digital form, with a certain amount of quantization noise for analog signals, obviously. So data structures could refer to each other recursively, and it was possible to create arbitrarily precise descriptions of complex objects in large sets of data structures in relationships. After 8 years happily learning and working, I discovered enough about the way the world worked to realize that my career choices were going to be rather limited if I didn't have a degree. So at 23, I went to university, and it was there that I came across the early research papers on Smalltalk from Alan Kay's group at Xerox PARC. At that stage, Smalltalk wasn't even based on the ASCII language. It had a lot of bizarre symbols inside it, but it embedded object-oriented principles, and it seemed quite natural to me that an object's description should include a list of its available behaviors. Smalltalk wasn't available in the UK, so instead I learned a language called Simula, an object-oriented simulation language that had actually inspired some of Smalltalk. It was a less exciting language, but it let me experiment with object-oriented concepts. After I graduated, I spent 3 or 4 years as a research assistant and building commercial systems, and then I started teaching computer science at Manchester University, and it was about a year into that job that I went on a research visit to the United States, and I visited Xerox's Palo Alto Research Center to return with a tape containing the Smalltalk 80 virtual machine. A research student and I implemented it by porting it onto the VAX 11750 with an early Three Rivers PERC workstation as the display. Unfortunately, practical experience with Smalltalk left me feeling it wasn't really a terribly expressive language. It wasn't easy to express algorithms the way that I wanted to, and that's ultimately what programming's about. It used this idea of message passing, which made the grammar rather awful. It was impossible to implement operator precedence, and the Smalltalk virtual machine was pretty much a hermetically sealed environment, so there was no easy way to communicate with the host operating system's resources like files and networks, for example. So for someone as practically minded as me, it seemed far from ideal. It seemed as though there wasn't really an object-oriented language or system that was approachable enough for widespread use. So for 10 years, I moved on into other areas, and I worked for a small startup called Sun Microsystems, created a business selling electronic publishing systems, and eventually became a consultant and a technical trainer. My training work increasingly took me to the United States, and one of the classes that I taught had used some Python, so I developed a certain curiosity about it. One evening, while I was waiting for a table, I came across a copy of Learning Python, and I bought it. And within 3 days of writing my first Python program, I was convinced that I'd found the language that would make object-oriented concepts accessible to a broad audience. I also liked that procedural programming seemed quite natural in Python, so I felt lots of people could understand it and use it. By that time, I was experienced enough in technology trends to realize that things don't succeed without considerable efforts being put behind them. And so I determined that I would spend 20 years working to make Python a widely known language. Interestingly enough, A lot of other people seem to have made similar decisions around that time, and many of them are still involved in Python's development now. So I'd finally found a programming language I loved, for which I've always been grateful to Guido van Rossum, Python's inventor and originator. So you might ask, what was it about Python that appealed so much to me? If you forced me to sum it up in a single sentence, I suppose I'd say, I like the language's elegance and economy of design. It has most of the things I liked about Smalltalk in it. It's modular, it's a dynamic language with late name binding. It uses exceptions, which I've always felt were an elegant way to handle complex control flows and error conditions. On top of that, it has sensible string handling and a judicious selection of basic data types. Unusually and somewhat controversially, the block structure of a program is indicated by indentation rather than using braces or keywords. Not quite sure where that came from. Braces or keywords, we didn't use those. In fact, I think it's still true. There's an Easter egg in Python. If you say import braces, import from future, import braces, it says something like not going to happen. It also has a standard library that gives access to network protocols, arbitrarily complex stored data, many other features, and the ability to package functionality in a very nicely modular form. Now, name-binding strategies are very important in determining the characteristics of a programming language. And Python specifically chose a late binding strategy. In C and other static languages, the compiler determines memory allocations in advance at compile time. That means it has to know the sizes of the values that are going to be stored in these named locations. So programs have to include type declarations for each variable. If a program needs to use memory dynamically, then it has to incorporate its own logic for doing that, typically using something like the malloc library. In Python and other dynamic languages, name bindings aren't set in advance. They're actually looked up at runtime. Variables are simply the names of references to data objects, which are automatically allocated from, the objects are automatically allocated from and returned to a storage heap without the programmer having to even think about that. Programmers don't have to concern themselves with memory allocation details at all. The data type's associated with the value, not the name, and because the name association is dynamic, polymorphism's quite easy to implement. Late name binding is, however, a mixed blessing. It dispenses with the necessity for declarations, and it makes polymorphism practical, but the need to look up names adds a significant overhead to execution time. So one of Python's fundamental principles is that readability is very important because code is read by people, not by computers. This emphasis on readability is a very important part of Python's appeal. There are basically two ways to design a language. You can either make it hard to write bad programs, or you can make it easy to write good ones. And Python very definitely votes for the latter camp. Sometimes we jokingly describe it as a language for consenting adults because it tries to give the programmer as much freedom as possible rather than trying to protect you from your own mistakes. By the way, I got an extra smile from this cartoon when I realized that the personnel manager couldn't spell either. So Guido van Rossum wasn't afraid to use concepts from other languages. This is a perfectly reasonable thing to do, given there's nothing really new under the sun. Python's object model is nowadays remarkably like Smalltalk's. The first and still the dominant Python implementation is written in C. And so, as you might expect, many of Python's early capabilities were, and indeed still are, based pretty directly on standard C libraries. Python's comprehensions were inspired by Haskell, its dictionaries by Perl hashes, and its scoping rules when they arrived by Lisp. There's no point at all trying to be novel just for the sake of it. If there are perfectly adequate solutions available, use them. And the genius, I think, of Python's design is that it weaves all these features together so naturally. Simplicity is also very, very important in programming. So when we compare the classical simplest program between C and, well, before I start talking about C, I am obliged to point out, first of all, that my C knowledge isn't current anymore. It's seriously out of date, so I don't claim these examples are necessarily best practice. And please consider my remarks about C not as being aimed at C in particular, but using it as a representative of static languages. But the C programmer in this simplest possible program still has to reference an include file without really knowing what it is, still has to write a procedure declaration, presumably as a beginner without having much idea of what a procedure is. So and the procedure has to have a specific name. It has to be called main. So in Python, the beginning programmer doesn't have to conform to any structure, doesn't have to make the solution any more complex than it really needs to be. Just print hello world. This is a very important point for beginners. Learning to program places a huge cognitive load on the learner. So by minimizing the initial load, Python lets people easily see some results and encourages them to try something a bit more ambitious. These slightly more complex programs show some other aspects of Python's simplicity. So on the left, we see the C and Python equivalents of that first little algol program that I wrote. And again, we've got the std.io calls, we've got the braces and the procedure. And you can see that in a C for loop, the programmer has to explicitly set the initial value of some counter variable. It has to give a condition that must be true for the loop body to execute. And it has to give an expression that should be evaluated after each iteration. Not only that, but even when that's done, the numeric value then has to explicitly be converted to a string before it can be communicated with the outside world. The Python programmer just iterates over an object that produces a series of integers and prints each one square. So the example on the example on the right, a slightly more complex example, shows even more how Python's for loop simplicity wins out. The C programmer has to say how many elements there are in the list, even though any sensible compiler would be able to count them. And when the list uses an object of a for loop, its length has to be repeated in the loop specifications. In Python, the program doesn't really care how long the list is. Each list knows how many elements it has in it. And then when it's used as the object of a for loop, the list, being a Python iterable, produces its members in sequence. So Python does very little in the way of implicit conversions, but all Python objects are capable of representing themselves as some kind of string. And so all the print function needs to do is ask the number how it should be represented as a string. Not only that, it's not shown here, but the elements of the list don't even need to be all the same type, and that blows people's minds occasionally. So another design principle is that errors shouldn't be fatal. When I started programming, And indeed, when Python was invented in 1989, it wasn't unusual for programming errors to result in messages that were completely inscrutable without investing a significant amount of time in understanding them. I remember my first PL1 core dump, which was about 30 sheets of printed information. It was absolutely horrifying. So Python basically handles whatever comes up, including errors from the operating system call or library routines, by raising exceptions. Programs can catch these exceptions and handle them with all kinds of appropriate behaviors. So at the lower right, you see here a simple recursive function. It's, in fact, the simplest recursive function you can define, since all it does is call itself. And then when I call that, or when that's called, the single call at top level to the function inside the try clause there causes an infinite recursion until the interpreter's recursion stack, or process call stack, is filled. That raises a recursion error. The recursion error is handled by printing a message, and the program continues. Try doing that in C. Another design principle is that performance is not the most important aspect of a programming language. Python's never really been obsessed with speed because it accepted the late name-binding overhead so early. It was obvious that execution efficiency was necessarily going to be key. Early users came to Python because of its utility rather than its speed. It proved very useful for writing network-based programs, for example. The original YouTube site was programmed almost exclusively in Python, although a lot of it's been converted now into other languages. It was relatively good at text handling. Its object-oriented capabilities made complex tasks easy, so people weren't too worried about efficiency. Python made some difficult tasks relatively simple. And there are many areas of computing where performance isn't especially important, and in areas like that, you can get a lot of utility with relatively poor performance. So even before Python started to move its performance over to the right, we were on the blue curve. So there was a lot of utility very early on in the history of the language. Python was also explicitly designed to be able to integrate code from other languages and from other code bases. And while there's sometimes been joking talk about Python's march towards world domination, in actual fact, Python has a very Catholic approach to computing. The Python world's happy to acknowledge that it is, as we might say in today's world, only one of your choices for programming language. And so while it'd be foolish to deny that many wheels have been reinvented in Python, there are some things which it's unlikely ever to be terrifically good at. One popular need among scientists and technologists is numerical computing, and for quite a long time, people felt that Python was totally unsuited to that. Of course, numerics have come to the fore as more and more scientists and technologists are finding a need to deploy computers in their work. Python was initially thought unsuitable because it allocates objects, including numerical objects, dynamically, and each one comes with a significant memory overhead. For large numerical computations, Python itself had no native way of working with these large arrays of dense numeric values packed into consecutive memory locations. Now, the numerical algorithms themselves have existed for a long time. The Nottingham Algorithms group, for example, was writing significant numerical algorithms in Fortran and maintaining a collection of numerical tools over 30 years ago. So with a great deal of work, the Python scientific community has, over time, collected those libraries and packaged them together. And you can now install whole collections of these things with a simple single command line, pip install numpy. Isn't life wonderful? Python also attracted itself to me by embracing its ability to give the user almost direct access to operating system capabilities and I/O. This helped programmers by offering a unified interface, and while each platform does have its own individual features, if you avoid platform-specific libraries, it's very easy to write portable Python. Many programs are written to determine a specific answer rather than for repeated execution, and so speed of development is, under many circumstances, a lot more important than maximum execution speed. And besides, Python's extensibility and ability to work with programs in other languages meant that performance could be pushed over or pushed out to other languages. Python developed fairly fast in its early years, and sometimes it made the occasional misstep. So, for example, the true keyword was introduced, if I remember correctly, in release 2.2.3, something like that. So Python 2.2 programmers had to resort to trying to reference the value true, the name true. And if that gave a name error, you would then define it yourself if you happen to be working with Python 2.2.1 or 2.2.2. Nowadays, we handle significant new features in Python rather more elegantly with the Future module, and as a quick demonstration of its capabilities here. In Python 2, that's the way that you would print the hello world program. In Python 2, print isn't a function, it's a keyword, and so it can only appear at the beginning of a statement. But if you import the print function from Future, then lo and behold, all of a sudden, the syntax of the language itself has changed. And it's for that reason, by the way, that Future imports always have to be the very first thing that you do. So that particular Future import was introduced in 2.6 because by that time the development team knew that print was going to be a function in Python 3, and they wanted people to start getting used to it. So programmers can actually gain experience with upcoming features. Another reason for Python's popularity is the huge range of applications. All the applications in the grid on the left are maintained by the NumFocus Foundation. The web's represented with Django and Flask and Bottle. All kinds of applications nowadays which are making scientists and other people's lives easier. Email is also actually an important application. It's said that Mailman handles about 1 message in every 6 that goes across the internet backbone. So this brief summary of Python's advantages might help to explain the multitude of implementations available. On the left, you actually see the smallest device I currently possess that runs Python. It's a D1 Mini based on the ESP8266 chip. And it's typical of an ever-expanding range of microcontroller devices that are supported by the MicroPython implementation, which is completely independent from the C core. Currently implements, I think, Python 3.4, which is very good. Python's being used to drive graphical processing units that offer the very fastest graphical and numerical performance available. So it's often used in rendering farms by companies like Disney. Even on classical CPUs, there are speed-ups available with tools like Number, Cython, and PyPy. And Python's quite at home running hugely parallel computations in the cloud. The fact that a single language can be well suited to such a wide range of environments and applications speaks far more eloquently than I can about the language's merits. If you're looking for a new language to experiment with, then I really would encourage you to try Python. Still banging the Python Software Foundation drum, I see. So that's today's summary about why I think Python's such a magnificent achievement. I feel that my 25 years younger self can be congratulated on choosing fairly wisely to invest so much time in Python. After all, if it weren't for Python, I wouldn't be here in Athens today. This graphic pretty well summarizes how Python's given purpose to my professional life, what I sometimes laughingly refer to as my career. Although I should remind everyone who's passionate about programming that people are still much more important than computers. My involvement with Python has brought me into contact with a large number of wonderful people, of a large group this weekend, and it's taken me to places that I never thought I'd get to. I enjoy software development so much because of the fascination of being able to, well, to almost build castles in the sky. Basically, if you can imagine a system driven by logical rules, then you can implement it in programming language and information systems. It's quite possible, although I don't know its complete origins, it's quite possible that the image on this slide existed first as some sort of data model which has been transformed by software into the visual representation we're sharing now. That's happening more and more. And indeed, the boundary between visual reality and falsity is being dangerously blurred. Python engages people's imaginations. It makes it possible for them to think about their programs in ways that make sense in terms of their problems. There are fewer details to keep track of, and as long as you choose your names sensibly, a good Python program seems to read naturally at a fairly high level. This freedom to create, though, does have a slightly dark side. Maybe the home of democracy is an appropriate place to wonder exactly what it is that capitalist democracies are building at the moment. It seems to me that we should abandon the hubristic assumption and somehow develop immunity from the law of unintended consequences. In my experience, software developers don't take kindly to the suggestion that they should accept responsibility for the creations. But I was just doing my job doesn't absolve anyone of responsibility. Being able to build something doesn't necessarily mean we should. Great power comes great responsibility. And I believe that either ethics will be our savior or their absence will be our ruin. But that's a subject for another talk altogether. Thank you very much for listening to my musings about Python. I was asked to save a little time for questions, and I believe we do have 10 minutes.
Thank you very much. Let's go for some questions. Right, there we are. What would you change in Python?
That would be a bit presumptuous. What would I change in Python? I don't think I'd change anything. I suppose, as far as I'm concerned, you could lose the async stuff altogether, and I really wouldn't miss it. But the Python developers, the core developers, have done an exceptionally good job of incorporating it into the language in such a way that people who don't want to use it don't need to bother about it, so I can't even really complain about that. What is your most recent Python project about? This is an interesting one. I'm currently working, for reasons I won't bore you with an electronics manufacturer who has a test jig that controls, basically they've got electronic equipment dropping off the production line and it all has to be tested. So they put it in a test jig, and this software, this Python program, manipulates the equipment to make sure that it works functionally. And basically it's a pile of spaghetti. So I'm pulling it out strand by strand, laying them all out on the desk, throwing about 3 in every 5 away, and rewriting that program. So it's nothing terribly high level, but it's good fun. Where do you see Python in the next few years? I suppose getting closer and closer to world domination. No, that's a fatuous answer, but I suppose the Python is just broadening its range of applicability all the time. It's difficult to think of an area that it's not going to be used in. I mean, people used to say, well, we'll never write device drivers in Python. Well, guess what? On my D1 Mini, I write interrupt handlers in Python. So that's something I didn't think 30 years ago I'd be going to do. Did you move in Python 3.x? I was very early onto the Python 3 train, if you like. I realized as soon as Guido made a formal move to say, the next release is going to be Python 3, I switched, basically, from 3.0 onwards, and 3.0 was a dreadful implementation. But it was 3.0, it was the first implementation. It was never going to be red hot. And so I was asked to write a series of 4 Python classes, about 160 hours of online tuition, and I wrote that in Python 3. When did I write those classes? Started in about 2006 or 7, I think, so very early on. I've not used Python 2 until this current project for about 10 years. Your opinion on the hint system on 3.5. Keep it optional. That's all. Just keep it optional. I'll be quite happy. Do you think Python should be an engineers-only weapon language? Well, I don't actually think about engineering in munitions terms, I suppose. But no, I don't think it should be an engineers-only language. I think an engineer, if they're working to engineering principles, should determine the language they use according to the characteristics of the problem. And there will be many things that Python's good for, but don't try and make it fit areas that it's not. If there's another tool available, use it. Why Python cannot become, if not as good as Go, in parallel processing? I don't know. Why does it need to be? I don't know. I mean, I've always, it's interesting. Guido said for a long time, for at least 18 years at least, he said, if you want to do parallel processing in Python, then use multiple processes, not multiple threads. But now, of course, we've got async, and he's drunk the Kool-Aid of that. So I've no idea why it can't be as good as Go. I don't know enough Go to be able to say. PEP 352, was it 352, 372? I can't remember. The new assignment expressions in 3.8, I think they're a wonderful thing. They will increase the expressivity of the language if used judiciously, and I'm fairly sure that people are going to do horrible things with it and then blame Python. Consenting adults language. Given how you ended your presentation, any comments about AI safety? Oh, well, obviously the same concerns as everybody else, that basically behavior is going to be behavior, and indeed existence is going to be normalized, so that if you don't fit the stereotype of the middle-class white Bay Area male, you're not going to be recognized as a full human being. And I think that's very dangerous, and I think we ought to be careful of it. Any languages that you think might threaten Python's dominant position in the future? No, probably it'll be the next language as popular as Python will be something that I'm not well educated enough or not recently educated enough to know much about.
Stephen,
yes.
How old are your grandkids?
How what?
How old are the grandkids? I think I saw on your profile and grandparent. Do your grandkids do they do Python?
Yeah, my son's about your age.
Okay.
My grandchildren are 8 and 5.
Okay, so have they started Python in school yet?
No.
Not yet. Okay.
No.
Okay.
No, I haven't tried. I didn't try to teach my son anything about computing, and I think he's a happier person for it.
Very good. Okay, Stephen, thank you very, very much for that.
Thanks, everybody.
All right.